Yes, this session is now recording. Welcome everyone to the sixth weekly discussion session for the Physics of Nanoscale Devices NPTEL course. My name is Jyotishwaran. I am a PhD student from the Department of Electronics and Computer Science, Indian Institute of Technology, Roorkee. So, in this week's session, we shall be essentially progressing with the idea of nodes and looking at the application of the notion of nodes to ballistic transport and thereby derive relations for ballistic currents and conductance and so on and so forth under specific conditions. So the notion of modes in ballistic channel was explored in the last session. So this is explored previously. And we've also solved some elementary problems there. And calculating the number of modes for a 2D channel is something that we have also seen. So this is W divided by lambda dB, 2W divided by lambda dB. And a kind of an explanation for the same was also given. Not an accurate explanation, fully accurate explanation, but the conceptual explanation where we kind of see where the quantum phenomena is kind of reflected in such a system. So today our first major point of like the first new topic for the day is the number of modes at T equal to 0 Kelvin. So this becomes a very important uh, concept for some very straightforward reasons. And then we shall be looking at the notion of ballistic conductance and the essential properties of it. And then through our explorations here, we shall also be looking at Fermi integrals and some basic properties of Fermi integrals. All right. So just a recap. The current through a ballistic channel is given by the following expression. And this quantity right here is the number of modes in the available in the channel. For a 2D channel, we have this expression for the number of modes. That is essentially arrived at by substituting the necessary values, plugging the necessary values into this particular expression where d of e is d2d of e into the area of the channel. Yes, so here I can clarify that. And this is essentially the inverse. The energy broadening is the inverse of the transit time. So gamma of E is going to be h bar upon tau of E, and d of E is going to be the area of the channel. This is length into width multiplied by m star by pi h bar squared. So if we plug in all these values over here, the respective terms will get cancelled out, and essentially we will get this quantity here, which is the representation of the, which is essentially L divided by tau of E. So that is the average transit time. So the average transit time divided by the length is going to give me the average velocity. So that is the way to arrive from here to here. And d2d of E to complete the thing is, yeah, so I had a minor confusion here last week. So I'm kind of, I hope this explanation will lay those confusions to rest. So we have this, and again, we have gone through the derivations that this m2d of E is also connected to the width of the channel. So I will just put an equal to here and write this is equal to W divided by lambda de Broglie of E further divided by 2. So this is also something that we have seen, and lambda dB of E is going to be h by square root of 2m E, m star E, because I know p squared upon 2m star, sorry, p squared upon 2m star, where m star is the effective mass, gives me the energy of the electron. So this is kind of what I'm plugging over here. So this is supposed to be h by p, and p I can write as square root of 2 m star E. So just to have a warm up, let us do a small problem first. So first the question is to calculate the number of ballistic modes in a number of modes in a 2D ballistic channel of width 10 nanometers at an energy of 0.1 electron volts. Okay, so let us see how to do that. And we have been told to, it has been given that we can assume that m star, the effective mass of the electron, is 1.1 ME. So we know that the number of modes m of E is this quantity. Just one second. Let me keep a calculator ready by the side so that I can also calculate these things in real time. Yeah. So, and over here I know this quantity is W, and I've been given energy E of the electron is EC plus 0.1. Now, how do I find what EC is? No information about that has been given. At least it would appear to be so. But we know that m star is equal to 1.1 ME. So at this point, I would like to address the idea of effective mass, which I kind of only briefly alluded to in our discussions in week 2. There was a reason because we had other topics to also catch up, so I didn't want to derail them. Now I will have a very small, uh, side discussion on the idea of effective mass. So, what is the notion of effective mass? So, we know m star is going to be h bar squared divided by d squared e upon dk squared. This expression is something that we know. But what is the meaning of this? Like, what does this give me? So, essentially, any particle or any particle of mass m in a solid can be treated as a free particle of mass m star. So that is the whole idea of the effective mass. So when we are considering the effective mass, for all intents and purposes, we are treating our particle as a free particle. So, and the effective mass depends on the curvature of the energy band. And this curvature is essentially measured at the band minima or band maxima. So this is a quantity that is measured at band edges. Okay. So either the minimum of the valence band or the maximum of the valence band or the minimum of the conduction band. In general, any point where the band achieves a maximum or a minima, I can define a finite quantity, finite value for the effective mass. Now, what does that mean? So this is an electron in the conduction band. So above the, yeah, I should have mentioned above the conduction band minimum. Above the conduction band minimum. Let me do one thing. Let me select all of this and just drag it down. Oh no, this is resizing it. Where is my move cursor? Yes, here is my move cursor. Yep, now I can do that. Conduction band minimum. So this is lying at 0.1 electron volts or 100 milli electron volts above the conduction band minima. Now I know any particle at the conduction band minima can be treated as a free particle of mass m star. Essentially, whatever crystal potential it is having, I'm averaging that. I'm kind of averaging over all those potential like forces, crystal forces that are being applied to treat it as a free particle of a slightly different mass. And this is the reason why sometimes we also get the idea of a negative effective mass when we look at the uh, holes in the valence band. That maybe we'll talk about them when we have a later discussion where both electron and hole currents become important. So again, I will make a small digression and address that topic briefly so that the reference is readily available for people who are browsing through the slides. Yeah, we have a new attendee joining us. So I shall just put a title here saying a small note on effective masses. And this is the idea of effective mass is not something that is introduced in quantum mechanics. The idea of effective mass is something that has been known since like the times of Archimedes. Like the whole idea of buoyancy principle is also essentially an effective mass. When a body is immersed in water, we say it feels lighter. So because of the buoyant force counteracting the gravitational force, the effective mass of the object becomes less. And if I dip a material that is less dense than water itself, then the buoyant force will actually exceed the gravitational force, and underwater, the object will move in the opposite direction to the gravitational force. So that is the situation where we have negative effective mass. And the explanation for the behavior of holes can also be done similarly. However, I will do it in a slightly more formal sense when the time arrives. So yeah, back to the problem. We know this is the expression. Now over here, I know lambda dB at this energy is going to give me is going to be h divided by square root of 2m star times E. So yes. Now since I've been given the effective mass, I know EC can actually be said to be 0, which implies any electron at zero point 0.1 electron volts above the conduction band minima can be treated as a free particle of mass m star with the same energy. So if EC is 0, then E is equal to 0.1 EV, sorry, 0.1 electron volts. Let me make a new slide. Yeah. So that implies lambda dB is going to be uh, yeah, sorry. Yeah, so this is going to be whatever. Yeah, h divided by 2 into 1.1 into 1.6. First, the mass of the electron, 9.1 into 10 to the power minus 31 into 0.1 into 1 electron volt. So that is going to be 1.609, the Coulomb constant, 10 to the power minus 19. So all of this will come out to be Just one second, let me calculate this value in just a second. So this is going to be a okay. So this will come out to be roughly 3.7 into 10 to the power minus 9 meters, which is 3.7 nanometers. So this is the effective, no, this is the Debye wavelength. So from this, I can calculate M of E to be equal to 10 nanometers, which was the original width of the channel, divided by 0.5 into 3.7, which is equal to 20 divided by 3.7. That will come out to be something close to 5. So yeah, this is going to be 5.4. No, there are no units here. Sorry. Yeah, so this is the answer. So this implies there are 5 modes. However, we can observe that lambda dB, which kind of plays the role of the mean free path. So this is the mean free path. Is actually very small compared to, it's not very small, it is smaller compared to the width of the channel. Now I don't know what the length of the channel is, so let us say I assume that this also has width. I'm just adding this now and length. So let us say this channel has a length of 10 nanometers. In that case, along with these modes, I will also need to calculate the transmission coefficient. So T of E is going to be lambda divided by lambda plus L. So this is going to be 3.7 divided by 13.7. So that will come out to be yeah. So this is going to come out to be 0.27. So in such a situation where I have a sorry where I have a 10 cross 10 nanometer cross 10 nanometer channel, 2D channel, what we see is, so if this is 10 nm and this is also 10 nm, then the effective number of channels, because of diffusive transport and all of that, the effective number of channels is going to come down to, it's going to be just 1, because T of E times M of E is going to be around 1.46. Effect of diffusive transport allows for only one ballistic mode. So what should be understood here is this current that is given here, this is strictly the ballistic current. So the diffusive current should be calculated using the diffusion equations. So this relationship here does not give us the value for the ballistic current. The total current is going to be I ballistic plus I diffusive. Okay, so essentially previously we had five modes for ballistic transport. But if the channel length were say 10 nanometers, then the effective number of ballistic modes that are available will actually come down to 1. So this should also give us an idea as to, if I know the rough electronic energies that are, the energy of the electrons that are moving through the channel, then that should give me an idea as to what is the proper width, so that I may have enough width and length dimensions of the channel, such that I have, the possibility of ballistic transport as opposed to diffusive transport. Okay. So this is, although a very simplistic approach, but nonetheless, this yields us very good qualitative estimates as to what dimensions our devices need to be. And at 10 nanometer, actually, ballistic transport does not dominate. To have good ballistic transport, like good ballistic character in the transport of electrons, we will have to move closer to the 5 nanometer region. So 5 nanometers or even some below 5 nanometers is where ballistic transport becomes really dominant. Between 5 to 10 nanometers, a good fraction of ballistic transport can be observed. So most of the relationships that we derive here will hold to an approximate extent between for channel lengths between 5 to 10 nanometers. Okay, so now we shall try to understand the idea of the number of modes in a ballistic channel at t equal to 0 Kelvin. So why is this important? So this will essentially allow us to identify the basic character of our channel. Now remember, how did we identify, or rather, yeah, we can say that. So what is the main, like the chief characteristic that we use to define silicon as a semiconductor? Now, why is silicon a semiconductor? So that is the question I'm asking. SI, intrinsic silicon, a semiconductor. Yeah, we can give several answers to this, but the definitive proper answer is at t equal to 0 Kelvin, there are no electrons in the conduction band. And even as we increase temperatures, we will need the electrons to be excited from the valence band across the band gap into the conduction band. So the only kind of current conduction that is going to take place is due to excitonic pairs that are formed under thermal excitation or any other method of excitation. So that is the characteristic property of semiconductor. So the very characteristic properties of an intrinsic semiconductor itself is connected to the behavior of the material at 0 Kelvin. Like we take a metal, like say mercury, at 0 Kelvin, it is still going to have conducting electrons available. In fact, mercury at 0, like we did not go to exactly 0 Kelvin. When as we are approaching 0 Kelvin, say, what is the critical temperature for mercury? I think it's around 2 Kelvin or something like that. So at around 2 Kelvin, it doesn't even act as a conductor, it actually becomes a superconductor. Like not only does it have electrons for conduction, they actually conduct without any resistance. So, but contrary-wise, if we look at a semiconductor like silicon, its conductivity will go lower and lower and lower as I lower the temperature. The conductivity of silicon increases with temperature. So the temperature coefficient of resistance will be negative for silicon. It is going to be positive for any other metal. So this property that allows us to distinguish between semimetals and metals, semiconductors and conductors, is actually the behavior of the material at 0 Kelvin or at very low temperatures. So by that reasoning, it is important to understand how our channel, which is essentially a structure, it is, some kind of a structure we build out of materials. In some cases, it is also built out of silicon, and see what kind of basic character does it have. Does it act as a conducting channel? Does it act as you know, a resistive channel? So that is something we will need to see and understand. Okay, so where are we? Yes, at very low temperatures, the number of the modes in the channel becomes strongly dependent on the carrier density in the channel. So ultimately, this is the quantity that is going to determine the number of modes that are available. Now, how do we characterize the number of carriers present in the channel just based on the temperature? So for that, we will use the idea of Fermi statistics. Just give me 1 second. Yeah, please come in. Yeah, sorry for the interruption. So this quantity is going to be uh, so this is, yeah, per centimeter square. So when I derive the kf value, it is going to be in inverse of centimeters. So this will come out to be into 10 to the power minus 5, like centimeter inverse. Now I know kf is equal to 2 pi by lambda f, which is the Debye wavelength at the Fermi level, which implies lambda f is going to be this quantity 2 pi by kf. kf. In fact, here I can just make a small shorthand to make the things simpler. Lambda f will therefore be 2 pi divided by square root of 2 pi ns. This is for a 2D channel. So this is equal to square root of 2 pi by ns. So I could have directly done this. So you know what, I'll just do that. Yeah. So just 1 second. Yeah. So this will come out to be, therefore lambda f is going to be 7.93 into not 3, 7.93 into 10 to the power minus 6 centimeters. So which is going to be equal to 7.93 into 10 to the power minus 8 meters, which is actually equal to 79.3 nanometers. Now, why is the Debye wavelength so large? Because at t equal to 0, the electrons don't have much energy. As the energy goes down, as you can see, um, where did I write that? Was it even before this? Yeah. So this is inversely proportional to the square root of the energy. As the energy decreases, the Debye wavelength increases. So at t equal to 0 Kelvin, this system has a uh, yeah, Debye wavelength of around 79.3 nanometers. Now the width of the channel was given to be 15 nanometers. So how many half wavelengths fit into this? Well, let us see. So the number of modes at EF is going to be uh, 2 into, yeah, 15 divided by 79.3. I can take this to be roughly 80, or you know what, just to be accurate, I can say 79.3 divided by, 15 divided by 79.3. This is going to come out to be 0.38, which implies there are 0 modes available for ballistic transport. Since there is no ballistic transport occurring here, no current is flowing, which implies the resistance of this channel is infinite. So such a channel can never be conducting, like it will only have conduction if electrons are forcefully excited into it. Like it will not be an intrinsically conducting channel. Yes, infinite. So I will either need to dope this channel or need to operate it at temperatures where there are sufficiently many electrons present in the channel. Now let us take an alternate scenario. So let me say, so an alternate. Let us keep all the values the same. And let me say instead of that, so let me say I have W is equal to 15 nanometers. And I say Ns is 10 to the power 16 per square centimeter. Now, how will the situation change in this case? So, first things first, lambda Fermi is going to be square root of 2 pi divided by Ns. So, this is going to give me yeah, wait. Oh no, 10 to the power 16 is way too high. Let me say instead of 10 to the power 16, yeah, because 10 to the power 16 per centimeter square is actually too high. Let me say I'm asking for something more reasonable, something along the lines of 10 to the power 14, which is 10,000 times as to what was present before. No, 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 no. Yeah, yes. So 10 to the power 14 electrons per centimeter square, or even I think I can reduce it by further also. Let us say I just have 1,000 times what was present. Let us say I just had 10 to the power 13 electrons. So 1,000 times what was initially present. I think that ought to give me a value that is more physically relevant. Yes. So now this will give me lambda s, which is lambda f to be 2.5 approximately into 10 to the power minus 7 centimeters, which is equal to 2.5 nanometers. So at this case, if I had a 15 nanometer channel, oh no, even now it's going to be too small. Yeah, so I should have taken something like 14 or 15. So let us say I will take something like 14. So this is going to be, yeah. So if I took it to be 10 to the power 14, then this quantity is going to be uh, again, same as before, 7 point, the initial part is going to be the same, 7.93 into 10 to the power minus 8 centimeters, which will give me approximately 0.8 nanometers. Yes. So this is now the Debye wavelength because there are so many electrons. EF is going to move up. Like in this figure, if I had more electrons, 1,000 times more electrons, then of course this EF will move above and above and above by a suitable amount, depending on the dimensionality of the channel. So that would mean I will have number of modes M of EF to be 2 into 15, 2 times W divided by 0.8. So that is going to be, that will come out to be 37.5. So 37 modes are present. So this gives us an idea as to like the number of modes. So if I had a 10 to the power 4, that is 10,000 times more electrons, then I will have 37 modes present. Alternatively, I can also reverse this calculation. I can find the situation essentially if lambda f was, or let me write that in a different color so that we understand. If lambda f is equal to 30 nanometers, this implies one mode is available. Which implies 30 equal to square root of 2 pi divided by ns. And from this I can say 30 into 30. So that is going to be 900 into 10 to the power minus 18 is equal to 2 pi by ns, which implies ns has to be, you know what, I will write this in centimeters squared so that we will get the proper unit. So 10 to the power minus 18 meters is going to be 10 to the power minus 16 centimeters. Correct? Yes. 10 to the power minus 16 centimeters. So now this is going to give me 2 pi divided by 900 into 10 to the power 16. So this will be zero. So this will come out to be something like approximately 7 into 10 to the power 13. So this is the minimum concentration of electrons my channel needs to have to allow a 2D channel needs to have to allow at least one ballistic mode of conduction, one mode for ballistic conduction. So this will kind of give us an idea as to what kind of materials we want to use because all materials cannot provide these many electrons. So if we took something like intrinsic silicon, that is what the value of 10 to the power 10 was, then we found out that the resulting channel will not conduct any current at 0 Kelvin. So there is going to be what is called a carrier freeze out. But if we had these many electrons, so if we can maybe dope the silicon or do further things, which we shall look at towards the end of the course, if there are further manipulations I can do to my material or, use a different material altogether, then this will give me a kind of target figure as to how many electrons I need to have in my channel so as to facilitate ballistic transport. So that is what this entire analysis that we have been doing so far has, allowed us to understand. Like this is kind of what we are understanding by looking at these things essentially. Okay, so yeah, so let us move to the next topic. Now, to understand the conductivity of a ballistic channel at low biases. So, when we say at low biases, I mean like the tacit implication is V is approximately zero, or rather V, I shouldn't say it is approximately zero, I should say V is tending to zero. So, in that case, I'm not going to go through the derivation. Our F2 minus F1 can be replaced by this quantity. So, or rather, okay, I will just briefly mention this rather than spend too much time on this. I will briefly mention what is happening here. Okay, so when I have this kind of a situation, and let us say again, we are even now we are only looking at a two-terminal device, and let me say I have a voltage V. Uh, I want current to flow from my source to my drain, but it's going to be the other way around. Yeah. I want electrons to move from my source to my drain. So yes, this is the direction. So let me say this is my source, this is my drain, and this is going to be minus then. Yeah, minus and plus over here. So I know that if I say EFS is equal to EF, let me say the source and drain materials are the same, then EFD, like the Fermi energy on the drain side, is equal to EFS minus Q times V. Now, if V is very small, this can be treated as a differential quantity, and F2 minus F1 can then be approximated using the derivative, first order approximation of the Fermi distribution function. Like the delta change in the Fermi distribution function can be written in terms of the derivative. And we have an additional property that we are writing as, just 1 second. Apologies, I'll have to take a short break. Yeah, really sorry for the repeated intrusions. Like there are some other events also taking place in the institute, so like people are moving in and out of the space where I'm working, uh, and because of that, we might have also missed around 15 minutes of the session in the recording. Like people who are attending in person got to see everything. So this video is minus 15 minutes of content. I will either have to re-record it and splice it back into the video, which I may not be able to do right now. So for now, the broken video will be uploaded to the YouTube playlist. Later on, like I know which parts I missed because, of course, I've been conducting the session continuously. So maybe down in the weeks, I will kind of re-record that part and see if I can get the video re-edited so that that part is included, and then upload the newer version. But right now we are going to have the broken version, but in any case the slides have the complete information, and whatever I'm discussing I'm also writing on the slides, so it should be fine more or less. Yeah, sorry about that. And for some reason I seem to have scrolled down also without my intention. So this is going to be like this. So this implies, again, just taking a small box for digression. This is going to tell me, so f s minus f d is going to be dou f times dou V, dou E multiplied by the difference, that is going to be minus Q times V. So minus QV. So this is what is going to be the value. However, there is another property where I have dou F by dou E. This part I will work out in the example problem is equal to negative dou F by dou EF, because the Fermi distribution function has two variables in it, the Fermi energy and the actual energy. Both of them can in principle be treated as independent quantities, because of course they are. The energy of the electron is the energy of the electron, it's a physical quantity, but the Fermi energy depends on the number of electrons and the configuration of the system, as discussed before, the volume of the system and so on and so forth. So I can have the same number of electrons and I can increase the volume of the system, or change the configuration of the system, and that will definitely cause a lowering or raising of the Fermi level in the given system. Or I can have the same system and inject more electrons into it, in which case again the Fermi level or the chemical potential is going to shift. So E and EF are not interdependent values, they are independent values. So I can do that. So this I kind of back substitute here, and the minus quantities cancel, and finally we will be left with this kind of an expression. And this quantity V no longer depends on any of the energy parameters, it can be taken out as a constant. So this entire quantity can now be seen as the specific conductance or conductivity at a particular energy. Integrating this over all energy values will give me the total conductivity, and the current is equal to the conductivity times the voltage. And at low enough temperatures, dou F of E by dou EF has this form, delta E minus EF. It becomes a delta function. And so since it becomes a delta function which is kind of at EF, then this integral, so let me also write that right here. Let me extend this box out a little bit. Oh, no, 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 no. Yes. Yeah. So at t equal to 0 k, dou F upon dou EF is equal to delta E minus EF. Since that is the case, plugging that over here, the delta function's property is when I have f of x times delta x minus x naught, when I integrate it in an interval that contains x naught, then I'm going to get f of x naught. So this implies integral m of e delta E minus EF is going to be m of EF. So the conductivity is only dependent on the number of modes at the Fermi level. This is a more quantitative explanation of the same phenomena that I described here. So this was the physical explanation where I said any voltage I apply is not going to excite any of the lower energy electrons. The only electrons that can be excited are the electrons in this region, near the Fermi energy. So that is the physical explanation. If you want a more mathematical explanation, well, we have it here. Take this expression, look at that, and we see that it becomes a delta function, and the only relevant mode is going to come down to this. And from this, we will also have specific values for the conductivity of the channel. Okay. Now let us look at another problem. Yeah. Yes. So yeah. So prove the following expression for all temperatures. So integral 0 to infinity dou f of a by dou e dE is equal to -1. So this is something we need to evaluate and prove. And then we also need the form of dou f by dou e at low temperatures. So let us start with this. So we have so what is this? So this is dou by dou e of 1 divided by 1 plus exponential E minus EF upon QBT. So when I want to take the partial derivative of this quantity, I will follow the chain rule. So this is equal to minus 1 divided by the square of this quantity, e to the power E minus EF upon QBT whole squared into the derivative of this quantity. One is a constant, so I will just write this as dou by dou E of e to the power E minus, you know what, why force myself to use the curly braces, E minus EF upon KBT. Now, I've already told that E and EF can be treated as independent variables, so I need not concern myself with that. The only derivative I need to consider is this factor of E divided by 1 by KBT. So this is going to be minus 1 divided by 1 plus e to the power E minus EF upon KBT whole squared into e to the power E minus EF upon KBT divided by, or rather into 1 by KBT. So this is the whole derivative. Now what I can further do over here is, or you know what, I don't have to do that. So to write the answer in the final form, dou F upon dou E is equal to e to the power E minus EF divided by KBT divided by KBT into 1 plus E minus EF whole squared. So this is what we have. This is the expression at any temperature. This is the general expression. Now what happens to this expression at lower temperatures? I can either do that by taking the necessary limits here, but rather than do that, I will consider a different, a more diagrammatic approach. So first let us integrate this quantity. Now integral 0 to infinity of dou f upon dou e dE. So I am going to integrate this with respect to that. So that is going to be integral of this quantity. I am not rewriting it again. Rather, what I will do is I will set y is equal to e to the power e minus ef upon kbt, which implies dy by d is equal to 1 upon kbt e minus ef kbt, because temperature is also independent of these parameters. I hope that part was obvious. So that would imply integral 0 to infinity dou E dE is equivalent to integral. I'll write the limits in just a minute. Uh, so this is this, so I can take the dE to that side. So this quantity into dE is dy. So what I will have is dy divided by 1 plus y squared. Yes. 1 plus y squared. Yes. So where y varies from, so when e is 0, what is the value of this quantity? So this will vary from when e goes to 0, this is going to vary from, this is going to be e to the power minus uh, ef by kbt. This is going to be e to the power minus ef by kbt. And when e tends to infinity, this quantity diverges to infinity. So this is going to go from some y0 to infinity, where y0 is equal to e to the power minus ef upon kbt. Yes. So yeah, this is the integral that we have. Now this is actually a standard integral whose value can be evaluated. Alternatively, what we can do is we can also take the complex approach where I can write 1 divided by 1 plus y squared to be 1 divided by 1 plus iota times y to 1 minus iota times y, essentially x squared minus y squared, where this will become 1 plus y squared. And then I can decompose this as partial fractions to give it, I think this is going to come up to be what? Uh, so that's going to be uh, 1 upon 2 iy, I suppose. So if I have to write this as a divided by this and b divided by that, so and stipulate that the numerator has to be 1, then keeping it as 1 and 1. Oh yeah, no, it's not even 1 upon 2i. Yeah, it's just this 1 plus iy plus 1 by 1 minus iy. So this is the quantity. So I can convert this real integral into a complex integral, and then I can show that this thing will achieve a singular value only when this point converges at 0. But y naught is always a non-zero quantity. So this is not equal to 0. This can never be 0. Even like this will only be 0 when EF tends to infinity. And typically we don't have cases where EF is infinity. EF is going to be a finite value at all times. So then this will become a contour integral, and from that I can say that this integral y naught to infinity dy divided by 1 plus y squared. There is a name for this integral, and I'm sorry I'm kind of blanking out on that. Maybe I'll maybe look it up after this lecture and maybe add the name of it to the slides. But yeah, this is how it is done. So I can back substitute this into this, and this particular integral will now become a complex integral, and then we can essentially use the we'll essentially calculate the residue for this, and the residue will always come out to be -1 in this case. So this quantity is equal to -1 for any given integration. The only case where this integral cannot be done is when equal to 0 for all finite values. of EF. And point to be noted here is for my system to have an infinite Fermi level. So I will make a small box here for EF to be infinite. Either n should be tending to infinity, I should have infinite electrons per unit volume, or alternatively, V should tend to zero. Like I should have my electron confined in a completely zero volume space. That is also not possible because we know that from Heisenberg uncertainty principle. So both of these scenarios are unrealistic. So EF is always going to be a finite value, no matter how we look at things. And therefore, this quantity is always going to be -1. So of this, we are guaranteed. Now let us come to the low temperature case. Okay. So, so now let us try to find out F by dou E at low temperatures. So whenever I say low temperatures, I imply this. Approximately 0 Kelvin, like very small values. So first, at very small values, let us plot the Fermi distribution function itself, because that is going to give us a very nice, for some strange reason, this automatic line drawing feature kind of is very buggy. Otherwise, my lines will indeed be very straight. Yeah, now it seems to be working. Yes, brilliant. Yeah, I figured this out recently and I've been practicing for the last few weeks. So, straighten up. Yeah, good. Now my figures look really good. And let me say my EF is over here. So this is my f of e. So f of e is equal to 1 if e is less than ef, and f of e is equal to 0 for all e greater than ef. So now what is this function? How do I represent this function? Like if I want to represent this as a closed form function, what is the method? So I hope many here are familiar with the theta function or the step function. So theta of x, it should be uppercase theta. So theta of x is, yeah, two cases, 0 for x less than 0 and 1 for x greater than equal to 0. So it's a function that takes a unit step at x equal to 0. Similarly, I can have theta x minus x naught where this 0 will be replaced by x naught. Essentially, whatever the argument is, if the argument is positive, it is going to be 1. If it is negative, it is going to be 0. Theta function can also be written as a ratio of the magnitude of a number divided by the actual value of the number, but see the actual number itself on the real line. But we shall not use that. We shall just use this definition. So from this, I know that this function vanishes over here. Like it is 0 for e negative also. Like let me assume I'm extending the axis to the negative side as well. Then the idea is that I have like I need a function that is 1 only in this range. So similarly, like if I write theta of minus x, then this symbol here is going to be flipped over. So I definitely don't want anything over here. Like anything for greater than EF, I want the function to be 0. So the first variable that I will consider is, first function that I will consider is, let me write it like this. So I want f of e at t equal to 0. So all of this is at t equal to 0 Kelvin. Okay. So over here, I can write f of e to be first theta of EF minus E. So as long as this quantity is positive, the function is going to be 1. As long as this quantity is negative, this function is going to be 0. So we can see that this quantity is going to be 1 between value E equal to EF and E equal to 0, and it also becomes 1 on the negative side. I need to do something to get rid of that. So now this function is definitely 0 for E greater than EF, because for E greater than EF, E minus EF will become negative and the theta function will bring it down. But this function also has negative values on this side. So this is not equal to 0 for E less than 0. So I need to get rid of that as well. To do that, what I'm going to do is I'm going to subtract this by, no, sorry, I'm going to subtract this by, yeah, theta, yeah, theta of minus E. Okay, I'm going to do this. So this will give me the total form of the uh, this is the form of the Fermi distribution function in terms of, like, a closed form expression, the theta functions. Now if I want to do dou f by dou e, it's going to be dou by dou e of this quantity af minus e and then minus dou by dou e of this quantity. However, what we need to understand is zero energy is kind of a, like, again, I can invoke quantum mechanics and say there is no zero energy state. Zero I can relatively choose as an approximation, or by taking effective masses and things like that. But what we have learned is when I have a confined quantized state, the energy can never reach zero value because of quantum fluctuations. So this particular region is actually irrelevant. So this quantity will kind of vanish over here. So this particular part of the derivative I can neglect. So this quantity here is neglected for physical reasons. Let me try to read this. The physical reason is that E equal to 0 is not a very realistic state. Okay, so the only quantity that matters is this. Now, what is the derivative of this function? The derivative of this function is actually the delta function. So let me, let me essentially put a partition here and say d by de or d by dx of the theta function is equal to delta of x. Same applies for any other delta function that we are considering. Any other theta function, x minus x naught will give me delta of x minus x naught. So this quantity here is going to give me this implies dou f by dou e is going to be just this derivative. So that is going to be, since I've taken the partial derivative, I have to do the chain rule also. So this is going to be minus of delta EF minus E. But there is also a property of the delta function where the delta function is an even function. So delta of x is equal to delta of minus x. So this is always true. So like it's a symmetric function, it's an even function. So this, I can just say it is equivalent to minus of E minus EF. So this is what we have mentioned here. Now remember, minus dou f by dou EF is dou f by dou E. Dou f by dou E is the minus Dirac delta function. So dou f by dou EF is going to be that multiplied by a minus. So I'm just going to get the Dirac delta function without a minus sign. So this is the form at low temperatures. Zero Kelvin. So this was the answer that we were looking for. And I also kind of did the derivative one step further to show why this is happening. Okay, so this kind of gives us the reason as to a mathematical intuition. I cannot call this the reason per se. The reason is always going to be the physical reason. Why does this not happen? Because this is the physical configuration of my system. This is the energetic configuration of my system. And I physically cannot excite a low because none of the higher energy states are directly available. If I am exciting it, I will have to send the precise quantum energy I need to excite an electron that is present here to an energy greater than the Fermi level. So that is not going to happen for every electron. But even when I apply a very small voltage, the electrons here will start responding to that at t equal to 0 Kelvin. So yeah, that brings us to the end of this problem, which finally I guess it brings us to, just one second. That will bring us to the end of the last problem that we are considering today. And this is going to be our introduction to the Fermi integral as well. So through this single problem, we are going to look at how to evaluate the conductivity at higher temperatures and what quantities are involved in that computation. In this course, now I can say this out loud. In this course, we are not particularly concerned with the evaluations. So this course is mostly conceptual. This is to essentially convey the concepts of nanoscale devices. We are not going to be doing precise calculations. We are not going to do any computational things. And in fact, the accurate evaluation of all these quantities can be done using techniques like density functional theory or other advanced techniques. We are not going to be focusing on them. The idea here is to use relatively simple concepts to kind of emphasize how to understand the complex behavior of these nanoscale, or rather complex behavior, how to understand the main central behavior aspects of nanoscale devices by using semi-classical treatments and relatively simple theories. Like the more accurate calculations need to be performed by using more advanced theories, but those conclusions are also going to be very much in line with what we are seeing here. Like whatever predictions we get here, they pretty much give the trend as to how these devices work. For instance, whatever I concluded here, that this is the minimum charge density, surface charge density required. Even if you use some DFT technique, you are going to find a value that is close to this. It is going to come out to be very close to this. Or, maybe one order of magnitude above or below. Like it's either going to be 10 times larger or 10 times smaller. So it is going to be very close to this area. So this gives us an estimate. And to perform this estimate, all I need to understand are the very basics of quantum mechanics. And all these calculations, as you can see, can be done on pen and paper. Okay, so there is the expression for a current in a 2D channel for low bias at non-zero temperatures, and identify the order of the Fermi integral that occurs in this equation. So let us begin. The current I is 2q squared upon h. So yeah, very quickly, this quantity right here, this is called the quantum of conductance. Why is this called the quantum of conductance? Because essentially, when I'm evaluating the current at low biases, I'm going to have this quantity multiplied by essentially the number of modes, because this is again a mode density function. Like this is the specific number of modes at a given energy, and this is actually a probability distribution function depending on the temperature. Because integral, as I've shown here, this quantity integrates to -1. So negative of this quantity integrates to 1. So this is actually a probability distribution function. That is also something we have inadvertently proven. So I will write that here, actually. Yeah. Therefore, minus dou f by dou e acts as a probability density function for conduction electrons. So yeah. So yes, so the quantity that I will get here, going back to this briefly, is going to be this multiplied by the average number of, or rather the effective number of modes available for conduction, multiplied by the voltage. So the conductivity of the channel is always going to be multiplied by an integer here and the voltage here. So this, the conductivity is always going to be an integer times this quantity. Since it is an integer times this quantity, this is the smallest value of conductance, hence this is the quantum of conductance. So this is the quantum of conductance, which is equal to the conductance of a single ballistic mode. Okay, so the value of this quantity will come out to be so this again has been done in class, but just for the sake of completeness, I will evaluate it again here. Oh, no, just one second. So yeah, this quantity, let me, this is equal to how much? This is going to be 7.75 into 10 to the power minus 5 mho, or the symbol for that, for conductivity. So it's, the alternate unit is also Siemens, but the Siemens, the, yeah, It's just the upside down omega symbol, which was the symbol for ohm. So this is the conductivity. This is equivalent to 12.9 kilo. So a single ballistic mode has this much resistance. So even when there is no collision happening, even when there is full ballistic transport, this is the amount of resistance the channel offers to any electron passing through it. And this resistance is effectively due to the energy gained at the, or rather, the energy that is dissipated at the source channel interface and the channel drain interface. So this again we have spoken about in the previous sessions. So coming back, so it is the quantum of conductance multiplied by this quantity m of e. So right now we are looking at purely ballistic transport. We are not including the effects of diffusion times dou f upon dou ef times v. So this is what we have. Yes. So this is what we have. Oh yeah, d. Oh my god, I forgot that. So we are integrating with respect to the energy. Now, how do we go about doing things for a 2D channel? For a 2D channel, we know what the number of modes is. So for a 2D channel, m of e we know to be twice the width of the channel divided by lambda dB and e, and this can further be simplified as 2w by h times square root of 2m star e. So because we are integrating with respect to energy, it is better to transform all quantities into their energy dependent forms. Therefore, I is equal to q squared upon h integral 2w on h square root of 2m star e into dou by dou e, dou by dou ef, uh, yes, dou by dou ef of the Fermi distribution function, which is 1 divided by 1 plus exponential e minus ef upon kbt. So this is what we have here. dE. In fact, I can even move the voltage sign over from here to here, so I can write I by V is equal to this quantity. Yes. Now, this partial derivative is independent of this integration, so I can actually move it out of my uh, integration. Like I can do it after the integration as well, because these are two independent operations which I can perform interchangeably. So let me extract all the constants out of this first. So now this is going to be 2q squared upon h, which let me call this g naught, just for reference. So I'm going to call this g0. Okay, so connection between g0 is this. Okay, so then what are the constants that I shall be getting out? So twice w divided by h into 2m star whole power half times dou by dou ef of e to the power half divided by 1 plus exponential of E minus EF divided by KBT D. So this is what we have. Now, what I can do is make the following variable transformation. So I can say eta should be equal to E by KBT, and subsequently I will say eta F, subsequently I will say eta F is equal to EF divided by KBT. Since this is the case, d eta by d is going to be 1 upon KBT, therefore d eta is going to be KBT times d. So, or d eta is going to be d by KBT, or hold on. Yeah, I can replace this by KBT times d eta. Yes. And similarly, though EF will also have a factor of KBT associated with that, because over here I can see that d eta F is going to be 1 over KBT. So both of those factors, I have a dE here and a 1 over dou F here. Both of those factors are going to cancel each other out. So what I shall be left with is the following. However, this E needs to be multiplied and divided by square root of KB. I hope you can see that. So this implies dE is equal to, sorry, yeah, dE is equal to KBT times d eta, and d eta F is equal to dEF divided by KBT. So the respective scaling factors here, if I multiply and divide by KBT, the KBT will get absorbed into this and become d eta, and the KBT that I'm having for division here will get absorbed into this and become d eta F. I hope that is correct. Just give me 1 second. So dEF is this. So there is going to be a 1 upon KBT here. Yes, and a KBT here, and they will cancel each other out. Yes. So I still have, but however, I need to turn this into eta, so I need to multiply by KBT to the power half. G0 into 2W divided by H, 2M star KBT. I'm essentially multiplying and dividing by KBT to the power half. When I divide E by KBT to the power half, this will become eta. So dou by dou eta F integral e to the power, sorry, eta to the power half divided by 1 plus exponential eta minus eta F d eta. So this is the conductivity G of the 2D channel. So all of these are the constants. So this is the quantum of conductance. Then we have these constants over here. And then we have this quantity here. This rescaled quantity. Now remember, if E varies from 0 to infinity, eta F also varies from 0 to infinity at a given temperature. So these limits do not change. These quantities are what we call the Fermi integrals. In fact, to be more precise, the formal definition of a Fermi integral is the following. So Fermi integral is written like this: f of eta f. Just 1 second, please. Yeah, apologies for the interruption once again. I hope we won't have any more interruptions for the rest of the session, and we have like 5 odd minutes to finish this off. So is given by the following. It's given by 1 by gamma of, oh yeah, I should say fk of eta is gamma of k plus 1 in integral 0 to infinity eta to the power k divided by 1 plus exponential eta minus eta f deta. So this is the uh, formula for the Fermi distribution function. Sorry, Fermi integral. So this is what is called a Fermi integral. Gamma is the gamma function over there. It is the generalization of factorials. So the gamma function is given by this integral. So gamma of k plus 1 is given by integral t to the power k e to the power minus t dt. So from 0 to infinity. So this quantity can be integrated by parts, and we can see that if k belongs to a positive integer z plus, oops, then gamma of k plus 1 is equal to k factorial. Like every time I integrate this from 0 to infinity, this will come out to be 1. So I will, if I do integration by parts, every time I will get a factor of k multiplying it. So I'll have k into k minus 1 into k minus 2 into so on and so forth. If I take it to be a general real number, then this integration needs to be done differently. It is actually an improper integral, and we essentially use complex techniques for this. Like for negative values it will have weird structures, but for positive values this is the definitely the generalization of the factorial. So this generalizes k factorial. So there are some standard properties for this. So some of the properties are as follows. Just one second. So the properties of the gamma function are, since it is a factorial, gamma of k plus 1 is going to be k times gamma of k, just like in factorial is n times n minus 1 factorial. And from this we can, and there is a special case of this result also. So we will have gamma of half is equal to pi. Sorry, not pi, square root of pi. So from this we can also find the gamma functions for half integers, because gamma of k plus 1 will be this. This will automatically imply gamma of 3 by 2 will be half times gamma half. So that's going to be root pi divided by 2. So, and like this I can increase it to 5 by 2 and so on and so forth. And I can also have it for negative integer values as well. Okay. So these are some properties of the gamma function. Now what do we have here? Oops. What do we have here? We have eta to the power half. So we need the the integral corresponding to the we have the integral corresponding to the uh, oh my God, why am I blanking out? Yes, we have the integral corresponding to k equal to half. So how do I arrive at that? I need to multiply and divide by gamma of half plus 1. And what is gamma of half plus 1? That is gamma of 3 by 2. That is root pi by 2. So let me make a new slide. Therefore, G is equal to G naught into 2W by H 2M star KBT whole power half into gamma plus 1, which is gamma 3 by 2, which is root 3 by root pi by 2, into dou by dou eta f of the Fermi integral of order half function of eta f. So this is what we have. And additionally, one more thing that we know is dou by dou eta f. Whenever I perform this differentiation, fk of eta f, we shall end up with, I think we will get k times, no, since I have the gamma function multiplied there already, I won't get anything. I will just have f of k minus 1 eta f. All the other normalization factors have been taken care of. So whenever I take the derivative with respect to the Fermi variable, the Fermi energy variable, then I will step down by one order. Since that is what is being done here, this expression is proportional to not f half, but f minus half of eta f, with the appropriate proportionality constants. So to answer this question, now we have the full expression here. We have written them in terms of the Fermi integral over here. And now we see that the relevant order of the Fermi integral is eta to the power, is eta to the power minus half. Therefore, Fermi integral of order minus half is what is used. Conductance of a 2D ballistic channel depends on f minus half of eta f. Why are we converting this into Fermi integrals? Because we are essentially, like, there are numerical ways for calculating these functions, and therefore we can, instead of performing the integration, just have a table lookup and substitute the appropriate values in these expressions. So that kind of takes care of the whole energy integration, and now the only thing that determines what we have is this quantity eta f. So once we know the Fermi energy, Fermi level of the system, then we can automatically evaluate the conductance of the system as well. So I think this is a good enough point to end today's session. Once again, I apologize for the chaotic circumstances, which kind of, let me see how many minutes I have probably lost. I have probably lost to the tune of, we've been going on for what, around 2 hours now. Yeah, we have lost just around 20 minutes. So there will be a 20-minute time skip in the video because, of, like, many people were walking in, so I had to pause the session and talk to them. And when I had paused the session, I forgot to unpause it after finishing the conversation with them. So I kind of missed some time. What I will do is I will go through this video again, see what part has been missed out, and at a later date. I may not be able to do it very quickly because for the next 2-3 weeks I also have a bunch of other commitments. But suffice it to say, the entire discussion is present in the slides, and I've taken the effort to write everything as clearly as possible. So if there are any doubts, please feel free to ask in the course Q&A forum. I'm going through them. Like, I'm also in touch with the regular TA of the course. So any questions you may have, either it will be answered by Parul or I myself shall answer them. And sometime down the line, I'll maybe add the properly re-edited video to the playlist so that the complete record of the session is present. So yeah, with that, I'll bring today's session to an end. I thank you all for attending and listening. We shall meet again, same time next week. Thank you.